Welcome to Hot Chips 29. Session 2, Internet of Things and Embedded.
So the term performance efficiency was used in the previous talks a few times. I guess the following presentations will show that performance efficiency in the context of IoT embedded means something different from performance efficiency in the context of GPUs. So this is the IoT session, IoT embedded session, I should say. My name is Jan-Willem van der Waard. I work for Cypress Semiconductor, and I will be your session chair. So we have two presentations. The first one is from SiFive. The presenter is Yunsup Lee. He's the company's CTO and co-founder. In addition, he acts as the chair of the technical committee of the RISC-V Foundation. Yunsup got his PhD from Berkeley, where he co-developed the RISC instruction set architecture and the first RISC-V microprocessors. His presentation is going to be on the SiFive Freedom SoCs. These SoCs are the first open source SoCs based on the RISC-V microprocessor. Yunsup?
Thank you so much. So really exciting to be here. Today I'm going to talk about SiFive Freedom SoCs, give you a bit of background on why we're doing this, and towards the end of the talk I'm going to give you some exciting announcements from SiFive. So let's dive into it. So take a look at these two graphs here. What comes to your mind? Well, I think our industry is in big trouble. Look at the total SoC development cost. It's been skyrocketing. And as a result, the design starts have been consistently going down. So I think this is really bad news because with less design starts, there will be less companies to share the development costs of a new node for the ecosystem. So for the ecosystem developers, they only have one choice to do, which is they have to make the upfront cost even higher. Well, higher upfront cost means less design starts. Less design starts means higher upfront costs. Well, that's a vicious cycle, and I think that's what has killed innovation in our industry. So to break the loop, our industry needs a fundamental change. And that's what I'm proposing today. I'm proposing a new industry-wide movement to bring innovation back, and I'm calling that the DesignShare Revolution. So how does it work? So in my mind, what I envision is the first step is to democratize access to IP. So make all IPs open source proprietary, available for free, or at reduced upfront costs. Let everyone who wants to build a chip give them a chance to succeed. And once we do that with these successful products, all the IP vendors who shared the risk up front will be able to share the rewards later on, as in the form of royalty payments and mass production milestone payments and such like that. Well, that's good. We can do that. But really, to push the design share economy to the next level, we need companies in the ecosystem which can take these design share IPs and turn them into silicon as quick as possible, as easy as possible, and as predictable as possible. So with that, my belief is that we all together can create new companies who can innovate without having to invest in full design teams and IP negotiation teams. Well, just like how the foundry model created an entirely new class of fabless semiconductor companies who didn't have to invest in a fab upfront. And I'm really excited to report that we've been making a lot of progress here, which I'm going to talk about. First and foremost, we've been making a lot of progress in RISC-V, a free and open instruction set architecture. So I'm really happy to say that we're experiencing rapid uptake in both industry and academia. And I don't need to explain to you why the microprocessors are important in a modern SoC, because all the components in the SoC are glued together with software. So to really enable the design share economy, we need a free and open instruction set architecture at the core of it. So there's many proprietary and open source core implementations out there which implements RISC-V. The software ecosystem has been growing very quickly. RISC-V support for binutils and GCC and FreeBSD has all been mainlined to their projects, and Linux and glibc support is just following. So now we have a nonprofit RISC-V foundation with 65+ and growing companies. So if your company logo is on this list, thank you for your support. Keep up the great work. If your company logo is not on the list, however, well, I'm sorry, you're missing out big time. So I would consider what's going on. The exciting news is that it's not just RISC-V on the open source hardware frontier. Some companies have started to realize the benefit of open source hardware. So Jensen Huang, CEO of NVIDIA, has recently shared his plans to open source the Deep Learning Accelerator, or DLA. So I don't want to put words in his mouth, so let me read his quote. In the recent GTC presentation, Jensen said, quote, "Why don't we accelerate adoption, democratize deep learning for the trillions of devices that will use deep learning?" And on a most recent interview with Barron's, Jensen said, quote, "RISC-V is an open source company, and they asked us if we might work with them to put our DLA into it, so we're going to give it to the community." Well, thanks NVIDIA, for open sourcing the DLA. And what I want to see is more companies joining this open source revolution to enable the design share economy. So that brings us to SiFive and the role that SiFive is playing in the design share economy. Well, this is what we do. We contribute to the open source Freedom SoC platform based on RISC-V. And so what that means is we have a well-maintained chip platform that you can take advantage of. You can just take it and make it better. So you can bring your sliver of innovation on top to the Freedom Platform SoC, and you can have a great product. So if you are an IP provider who has great IP technology, bring it to the Freedom Platform. SiFive will help you find customers and new markets for your IP. If you are a system designer who has a great idea and are very frustrated because you can't build a chip, I know all of you guys out here have great ideas, come to SiFive. Start customizing the Freedom SoC. And once you're happy with it, just send us the requirements. SiFive will take care of the rest. That means you bring the requirements to us, and we'll take care of the rest. Fab, pushing it through the flow. We take care of manufacturing, we take care of packaging, we take care of testing, we take care of all the logistics. It's as simple as that. So again, system designer, bring us requirements. We sell you back packaged, tested, Freedom custom chips, which is yours. So let's do a more deep dive for the SiFive products here. So we have two platforms for the Freedom SoCs. The first line is a Freedom Everywhere platform. The second line is a Freedom Unleashed platform. So the Freedom Everywhere is designed for low-power 32-bit microcontrollers manufactured in 180 nanometer. The target markets are edge computing, smart IoT, machine learning, and wearables. The Freedom Unleashed platform is designed for high-performance 64-bit multi-core SoCs manufactured in TSMC 28 nanometers. We've done all the hard work to onboard high-speed peripherals such as PCI Gen 3, Gigabit Ethernet, DDR3 and 4. We also have places where you can add your cache coherent accelerators into the SoC. The target markets are data center accelerators, storage, SSD controllers, networking, and baseband. We also have a set of Coreplex IP products for the people who are building chips the traditional way. We're happy to support you guys, but that's not the focus of the talk. So if you're more interested in our Coreplex IP products, please go to our website. But today, we're going to focus on the Freedom SoCs. OK, I'm going to switch gears, talk a little bit about our Freedom Everywhere platform, our low-power 32-bit microcontrollers. So this is the Freedom Everywhere 310 chip, or the FV310 chip. So the reason why we built this chip is to validate all the IPs that we onboarded on the Freedom Everywhere platform. And there's a whole tray of FE310s. So here's the deal. We've already done the hard work onboarding IPs onto our platform. You don't need to reinvent the wheel. Take advantage of all the hard work we did. Just bring your sliver of innovation. And then you can start customize the Freedom Everywhere platform. Come to us. We'll work together to build a chip for you. So what's inside the FE310 chip? So at the heart of the FE310 chip, there's the 320 megahertz SiFive E31 CPU, which performs 1.61 dBits per megahertz. We have 16 kilobytes of L1 instruction cache, 16 kilobytes of scratch pad. We have onboarded a bunch of low-speed peripherals like GPIO, UART, PWM, QSPI. Also work with third-party vendors to enable OTP, mask ROM, clock generation, which can take a wide range of clock inputs. Also have always-on domain. So we also support low-power standby. It's manufactured in TSMC 180G. It's packaged in a 6mm by 6mm 48-pin QFN. So here's a close-up shot for a chip and our GDS plot. It's a 6 square millimeter chip in TSMC 180. You can see the nice regular structures for the SRAMs, for the instruction cache and tag, the OTP, the mask ROM, and the PLLs. So take advantage of all the hard work we've done. We've gone through our process technology node, metal stack. I've gone through this once. It's very, very hard to figure out what works all together. We've done all the hard work, so just come and leverage all the work we've done for you. So for the people who are interested in the performance and power of the Freedom Everywhere chip, so we went and compared the FE310 chip with an Intel microcontroller and an ARM microcontroller, which are all built and manufactured in the same TSMC 180 nanometer process technology node. We measure performance. It's about 10x faster than all microcontrollers, 9x more power efficient than the Intel Quark, 2x more efficient than the ARM Cortex-M series. So, I mean, it's a pretty good baseline to start. Just come and take advantage of all the hard work we've done. So we also built a development board with our FE310 chip. It's called Hi-Fi 1. It's an Arduino-compatible RISC-V development kit. We've already sold 1,000 copies of it to 40 countries. It's a pretty good starting point if you're interested in the Freedom Everywhere platform. It's only $59. You can go buy it on Crowd Supply. So I'm going to talk a little bit about the Freedom Unleashed SoCs. It's our 64-bit multi-core SoCs for embedded computing. Well, this is one of our first announcements. So I'm really happy to share this. It's the first time we're talking about this. This is our Freedom Unleashed 500 chip. It's our instantiation of our Freedom Unleashed base platform. It's implemented in TSMC 28 nanometers. At the heart of this base platform, there's the U54 multi-core CoreFlex with 4 U54 cores and 1 E51 core. The U54 cores support single precision and double precision floating point and is able to boot a modern operating system. The private L1 caches are backed by a banked L2 cache, which implements directory-based cache coherence. And the L2 cache is backed by a DDR3-4 controller and PHY combination. We've done all the hard work onboarding the DDR controller and PHY, as well as the low-speed peripherals, the OTP, the mask ROM, the gigabit Ethernet, a bunch of clock generation units. You might have noticed that all the components in our chip are interconnected with something called TieLink. It's a free and open SoC interconnect that we are supporting. We put all the specs out there, all the open source implementations for crossbars, adapters to AXI4, AHB, APB. Everything is open source. Just come and take advantage of it. So for this chip, we also built ChipLink, which is a serialized version of TieLink. So we're tunneling the TieLink from the chip into the FPGA. So you can attach this chip to an FPGA and put a TieLink switch there. And you can take this FPGA and put your IP inside to prototype with this platform. You can put your IP in the FPGA, and before you come to us to tape it out, you can attach it to the chip, and you can start prototyping it. Also, PCIe USB MIPI is supported in this way from the FPGA, so you put that on the FPGA and connect things with ChipLink. This is a GDS shot of our Freedom U500 chip. It's about 30 square millimeters in TSMC 28. It integrates 250 million transistors. So in the middle, you can see the 4 U54 cores and 1 E51 core. The U54 cores have 32 kilobytes of instruction and data cache, supports ECC. On the bottom, you can see the 2 megabyte L2 cache also supports ECC. On the right-hand side, you can see a 72-bit DDR interface, the PHY and the controller. On the left, you can see chip link. On the top, you can see the gigabit Ethernet OTP. Again, the deal is, heard it so many times, you've done all the hard work, integrating all the IPs, just take advantage of it. Bring your sliver of innovation and sprinkle it on top of it, and boom, you have your own 28-nanometer chip. So this is implemented in TSMC 28 HPC. We'll have a flip chip BGA package. The development boards with the Freedom Unleashed 500 chip will be available in Q1 2018. OK. Let's talk a little bit about our open sourcing efforts for the Freedom SoCs. So remember, the reason why we open source the Freedom platform is to make your job easy as possible so that you can take all the work we've done and go and customize it. So we have emphasized our FPGA support of the Freedom platform. So you can take the RTL of the RISC-V CPU generators, the tie-link. Oh, by the way, the free and open coherent SoC interconnect, the tie-link specs are all on our website. So if you're interested, please go take a look. So the implementations of tie-link, you can find it online, low-speed peripherals as well. We also have support for high-speed Xilinx FPGA peripheral wrappers like DDR and PCIe. So check out dev.sifive.com, SiFive's GitHub organization, and Free Chips Project GitHub organization. However, I'd like to note that the third-party IPs like PADS, PLL, OTP, ROM, which we signed third-party NDAs, those are not available on the FPGAs. You can only take advantage of those once you build chips with us. It's a checkbox for our Freedom platform. So with these FPGA dev kits, what you can do is take the RTL and synthesize it yourself and put it on the board. So the picture on the left is the Freedom Everywhere 300 platform mapped to the RD FPGA development kit. The one in the middle is the Freedom U500 platform mapped to a VC707 FPGA dev kit. Since the FPGA has PCIe, we attach a bunch of PCIe devices like a SSD hard drive, a Ethernet card, a graphics card. And now you can see Doom is working on a RISC-V computer here, because Doom is also open source. So if you're used to more IDE-type software development environments, we also have Freedom Studio, which is our open source version of the Eclipse, which supports RISC-V and SiFive CPUs. So every so often, I get asked, why did you open source the Freedom platform? Well, what I'm trying to do, my short answer is we're trying to copy the success of open source in software, and we're trying to apply that to hardware. Look at how valuable businesses the software our colleagues made. You know, I think Mike Taylor said that, but Instagram became $1 billion with 15 people. How did they do that? Well, they leveraged a lot of the open source things out there. People don't build the same things again and again and again. Unfortunately, I think our hardware industry is nothing like that. Everyone reinvents the wheel again and again and again. And I think we can really change this so that developers and IP providers can focus on their value-added innovation. We can enable both open source developers, but also for-profit IP companies. So we can leverage the collective effort of the community and industry all together. So that the goal is system designers who have great ideas. I know a lot of you in the audience have great ideas. You think you can make a better part. We're trying to enable you guys. Trying to let you guys easily customize your own chip based on the Freedom platform. So this is the second announcement, and I'm really excited to talk about this. It's the first DesignShare IP partnership that SiFive made with Rambus. So SiFive and Rambus are partnering together to deliver end-to-end security solutions. So if your application needs anything, something like a cryptographic core, hardware root of trust, key provisioning, you're covered. Come to SiFive, we have prepackaged IP that is already onboarded on the Freedom platform at a minimal upfront cost. So they can build a chip with Rambus's security cores. And the great thing is you can pay for the services later on. So hopefully by now, I've convinced you to join the DesignShare revolution. If you are an IP designer who have great technology, work with us to onboard your technology onto the Freedom SoC platform. We will find new customers and markets together. If you are a system designer who has a great idea to build a chip, I'm here to tell you you can afford a custom chip today with SiFive. So start customizing the SiFive Freedom SoC platform and innovate both at the hardware and software. So as an industry in all, let's lower the upfront cost and increase the design starts together to bring back innovation. So start today at SiFive.com. Thank you very much.
Okay, we've got time for some questions. Go ahead.
Nathan Brookwood from Insight 64. Curious about two things. One, what's the business model? You're open sourcing all this, so how do you make money? And secondly, Rambus is not a company that typically gives away its IP, so how does that joint relationship work?
I think I can answer the first question. Well, again, the system designer gives us requirements, and we take care of the rest. So we're selling package-tested quality chips back to the system designer, and that's how we make money.
Could you repeat that again? I'm not sure I followed.
We're selling a custom package-tested quality Freedom SoC back to the system designer. The system designer can place an order with 1 million parts in, and then we will deliver the 1 million parts at a certain price. And it's as simple as that.
So you're the interface between the system designer and the foundry.
That's right. Speaking of Rambus, I mean, I can't speak on behalf of Rambus, but here's what I think is happening. So there are downstream services that Rambus can monetize on. So I think that's what's going on. And for other IP customers who have onboarded on the DesignShare IP program, what happens is once you sell the chip and once they scale, we can go and pay the royalties later on. So they're investing in the customer success.
And is the relationship between the customer who's using the Rambus IP with Rambus, or are you the middleman?
No, this customer only deals with us.
So all the Rambus, you're the middleman for the Rambus IP?
That's right.
Ah, thank you.
Okay.
Okay.
Question from this side.
Yeah, I'm Oliver Gunasekara from NG Codec. I like the model, but 28 nanometer isn't really state of the art any longer. What are your plans for more advanced nodes?
Yeah, I get that question a lot. But I think 28 nanometer is a great node for a lot of people, especially for the people who has been frustrated because they can't get access to custom silicon. For them, 28 nanometer is godsend.
Yeah, well, I'd like to work with you on a 16 nanometer plan.
Great. I will collect feedback. I'll take that into account. Thank you. Question from this side.
Hi, this is Trivikram from Google. So I think I understand part of your vision, but I have a hard time trying to figure out how you're going to step up the value chain and still kind of stick to your democratization of access model. Specifically, I see you guys have done a lot of work, obviously, in the instruction set architecture. Also trying to sort of standardize methodologies, system design aspects of it, compilers, obviously. What about microarchitecture? What kind of work have you done on, microarchitectural innovation? Because in my view, you might want to democratize all you want, but if you're not adding any, value, it still has value, but it's not going to evolve further. So specifically, microarchitecture, and especially as Moore's law is slowing down, what are your plans to sort of get more out of your transistors and do that in a democratic fashion?
That's many questions. Let me try to answer all of them. Frankly speaking, the reason why this model is going to work right now is because Moore's law has been slowing down significantly. 20-nanometer technology node is going to be a very good technology node for quite a while, and that's how we get a lot of use out of it. So that's that. Second question about microarchitecture is, I think the reason why people were obsessed by microarchitecture and pushing the frequency is because people were selling standard parts. How do you differentiate from your previous part? Well, you need a better microarchitecture. You need better clock frequency and such. But once we change this model like this, and when you enable people to bring their own IP to build a chip, I don't think the microarchitecture of the CPU will matter that much for them. Because you're already accelerating the part that you care about 10x, 100x. Who cares about the CPU? I mean, they care about it, but they care less about it.
Okay, follow-up question.
No, I would like to go to the other side of the room. We have 1 minute left. Yeah, and you can follow up in the break. Thank you.
Shagal on Cavium. You used Drystone for performance comparison. Have you run any other type of software, and is it following the same metrics?
Yes. Yes, we do. The reason why we reported Drystone numbers is because a lot of people ask that question because I guess they're used to, I mean, I don't think this is the greatest benchmark numbers, but we're going to share our numbers once we've got our chip back and we validate the numbers.
Okay, thank you.
Okay, I got 10 seconds left. So if I want a freedom everywhere SoC with embedded flash in 118 nanometers, do you have those macros available?
The embedded flash?
Yes. Typically, microcontrollers have embedded flash.
That's a great question. We don't have it today, but we've been in discussions, and we've been collecting requirements from a lot of customers, and that is very top on the list. So that's something that we're going to work on next.
Great to hear that. Okay, thank you. Let's thank the speaker. Okay, over to the next presentation from ETA Compute. The presenter is Dave Barker. Dave is a fellow at ETA Compute, and he develops asynchronous processors. Before ETA Compute, he worked at a couple of companies, and we'll just list a few. One was Embic Micro, where he did low-power ARM Cortex-M implementations. Green Hill Software, Equator Technologies, Compaq Computers, and IBM. Dave received his PhD from the University of Texas at Austin, and he currently has 40 patents issued. So Dave is going to talk about an extreme low power implementation of an ARM M-class processor. Dave?
Thank you, Jan Willem. Yeah. So I learned something about product positioning today. I'm on a session where I followed 2 really large GPUs. I followed SiFive's discussion on a multi-core RISC-V system. And now I'd like to talk to you about a Cortex-M3. So let's talk about why we would do that. The motivation is that if you're going to deploy billions of sensors to the edge nodes of the IoT networks, well, we all know that low cost is important, and we all know when we're working on small size, and we all know that robust operation in unfriendly environments is going to have to be dealt with. You've got a standardized hardware so you can afford to make software. And you have to use an ARM processor and standard wireless, or you'll never get the thing to market. But what we're really not all working on is removing the battery. And that's basically what ETA Compute has been doing. That's what we're working on. And that's what I'll be talking to you about. Let's see if I can make this thing work. There we go. So there are issues with batteries. Most of you have a smoke detector in your home. You know what I'm talking about. You have to replace that battery quite often. Too often, from what I hear. So batteries have some issues. You can see on the right-hand side of this picture that recycling batteries is an important thing to do. We free up and deplete billions of batteries every year, and way too many of them go into landfills. We've got to stop that sort of thing. They also have some other difficulties. So if you have extreme temperature ranges to deal with, you find that batteries are not very helpful below about 0 degrees C. they trail off pretty quickly. Above 85, the shelf life goes away. So batteries are not easy to work with or to depend on, and they certainly have limited capacity. So what we've been working on is energy harvested applications and SoCs that are aimed at working within an energy harvesting window of power. So, you basically have 100 microwatts with a reasonable sized solar cell, photovoltaic cell. I shouldn't call it a solar cell in here because obviously it's not exposed to the sun. But a PV cell that's of reasonable size, you get about 100 microwatts of available power. Not many GPUs going to run on that. So we have a new paradigm for you. Everybody is familiar with the conventional wisdom. The conventional wisdom is race to idle. And by this, you can see from this diagram, we have these moments of intense activity separated by sheer boredom. So at least that's the way we think about it when we're doing software for them. So in order to minimize usage, what people try to do is duty cycle very fast processors. So they'll run at the maximum frequency they can achieve for a few hundreds of microseconds, maybe as much as a millisecond, and then they'll sleep for a long time. You'll see duty cycles for this of 1%. You probably will see duty cycles of 0.1%, that sort of thing. Anything they can think of to find ways to minimize power. But there's a problem with this, and every time you go from asleep, powered down, to fully awake at high voltage and running at high frequencies, you have to first charge up an LC circuit and a buck or buck boost converter to where you get that high voltage, and then you've got to spend some time bringing up and stabilizing a high frequency clock for that thing too. So you end up with these orange triangles on the left showing you going from sleep to wake, and these times can be anywhere from 15 to 25 microseconds. So it's a long time that it takes you to get started. And you think that you go instantly back to sleep, and you certainly do, but you're wasting energy on the backside as well because you have this tank circuit, this LC that you've been using for the buck that's full of energy, and it has to be depleted, and it's energy that you never got to use. So there's these two kinds of efficiencies that are a bit of a problem with this, what I call jackrabbit mode. We have an alternate approach called the always-on approach. My marketing team hates it when I say this, but it's the tortoise approach compared to the jackrabbit approach. So basically what we do, instead of doing these moments of brief and intense fury, we actually just run at a low, steady rate, just like the tortoise, for all time. We basically will run at 250 kilohertz for the full time, and we'll get the same amount of work done, but we won't have done all the pre-charge and discharge operations to get to high voltages, and we won't have wasted all of that energy in doing buck boost transitions. So we run at 0.3 volts in 90 nanometers. That's way sub-threshold. So I'm talking today about how we achieve that. If you're in the race to idle world and you're doing software, there's some nasty things you have to deal with. Here's a modes chart from, I think, Energy Micro. This is basically the different low power modes or sleep modes that you have to pay attention to with your software architecture. And you have to look at the transition times between them because these transition times are staggeringly large. So other things that you have to worry about as a software developer is you have to familiarize yourself with all the different kinds of clocks you're going to be facing. You have to organize your code to minimize wake-ups. And Embed has recently done a lot of power savings by combining interrupts, so they don't even wake up and interrupt things except in sort of coordinated ways. These are very unnatural things for an application to be thinking about and doing, and so it's difficult to do that. With the always-on approach, if you decide to run in a power-constrained mode, you look and see what your PV system can supply, and you just say, I'm going to set my voltage for that power level, and I'll get as much work done as I can, and if I can't get it all done, I'm going to pitch some function out. The other approach is performance constrained, and you say, I need a certain number of MIPS to get this job done, and I'm going to dial the voltage in until I get that MIPS. And you can do that with our dial logic, which we'll talk about next. So there are a lot of challenges in designing for deep subthreshold. If you really want to go subthreshold with logic, or even near threshold, you're going to have to deal with models that are not very friendly. You're going to have to deal with large delay variations over the volume of PVT. You're going to have to worry about the fact that distributions are not very friendly for those delays, and the fact that two gates side by side each other may have drastically different performance characteristics. So all of these things are very difficult to deal with in a clock design and to close timing, setup and hold type timing. My friends at Ambic, Scott Hansen and his team, are probably the best in the world at dealing with this. And they know how difficult it is. This is a very tough problem to yield lots and lots and lots of devices that freely run within all of the space of PVT. What we like about what we're doing is we never worry about setup time. We never worry about hold time. These are not issues for us, which makes it possible for us to slide in and out of subthreshold ranges of voltage without doing a reset. We just keep running. So the dial architecture, that's delay insensitive asynchronous logic, is a way to take clock logic like what you see on top. You see a pipeline with Boolean logic in between register stages. Well, we like to take that and turn it into asynchronous logic pieces of a pipeline, and we do that with some tool automation that we have. So we can take Verilog, always at pause edge type definitions of pipeline stages, and automatically convert it to asynchronous logic based on our dial technology. And once we've done that, we can grab the voltage knob and we can turn the voltage down. In 90 nanometers, we can go down to 0.25 volts smoothly. I'm going to show you a video towards the end of us slewing voltage between 0.25 volts and 1.2 volts, just continually watching the frequency change of our operation. So we have complete dynamic voltage scaling implemented here. So the block on the bottom is actually an asynchronous pipeline. The squares represent delay insensitive latches or flip-flops, and the stuff in between is conventional logic expressed as dial logic. And each one of those stages is self-timed. That is to say, when a stage completes, it knows that it's got valid data, and it moves on to the next operation. It sends a notice back to the previous stage that says it can also move on to the next operation. So what happens is the pipeline runs at the slowest stage rate that you've got, so it's easy to rebalance. You just kind of move things around until you get the right mix of processing, because remember I said there is no setup and hold time thing to worry about here. All you have to worry about is performance time. So our methodology, we use cadence flows for everything that we're doing, is we can take customer RTL, or in the case of what I'm going to show you, we've taken the ARM M3 RTL, and we've run it through our tool chain at number 1, and we get out of that a gate net list of asynchronous logic. Now we have formal verification methods to make sure that those two are matching, and we use Cadence Jasper Gold to do that. We can also simulate both of those and get comparative results. The system on the right with the functional asynchronous logic is going to be identical to the function on the left in function, but its performance may vary. So you may see it running 1/10 the speed of the simulation on the left with the right SDF file, or you may see it running 10 times faster. So you have to deal with these frequency differences, but if you take that into account, functionally these two simulations match exactly. The other thing that we've brought to the table is a special circuit design library. We have a library of asynchronous gates that we can implement dial logic in, and these will go from, like I said, 1.2 volts all the way down to 0.25 volts, 90 nanometers. The library itself, well, we've done several of them. We've done one at 180, we've done some at 130, we've got one at 90, and we have one at 55 nanometers. And so we've got all of these libraries that we can synthesize to that allow us to run over these great ranges. So deep subthreshold operation is quite practical with this approach, and that's where we like to run. We like to run deep and run slow and run always on. So we've used this logic to build an SoC, and it allows our processor operation down to 0.25 volts. And it's robust across temperature and all kinds of voltage changes. So we're not hitting the reset button as we go every time. Now this eye test chart, I'm just putting it up here so I can talk to you about it briefly. When you get your electronic copies and you study it and you have questions about it, my contact information is there too. Don't hesitate to call me. But for now, what I'm going to point out is that at 0.25 volts, we have designed this library for more than 5% static noise margin, even down at 0.25 volts. We've also done some test chips. We did a test chip with a whopping big 32-bit counter on it. This was a chip that was designed to look at the libraries. It was designed to look at the operation of the gates themselves, and also to give us a vehicle to characterize the library. And so we did that, and what you'll see in the chart on the right, which is an eye test here, but you can look at it in detail, is the green curve on the right is our estimate. The continuous curve is our estimate of what the performance would be in terms of power, And the blue curve on the left is our estimate of what the performance would be in terms of frequency. And the little dots, which I hope you can see up there, are the measured characterization data we got back from this. And we were extremely shocked, actually, to see that they laid so closely on our prediction curves. But the characterization data for this was really pretty astounding. And like I say, if you have questions on this, detailed questions, you can catch me at lunch or you can email me or call me. But you can't build a vision of IP without more of an ecosystem to support it. So we have this low voltage delay and sensitive logic, but we need some other pieces around it. So we have designed and ported some other digital circuits. We have a chip that's taping out within a few weeks that has a cool flux DSP on it in dial logic. We have real-time clocks that we've converted for ultra-low power. We have AES blocks and other fixed function blocks that we've converted. But the most interesting thing we've done in this chip is we have ADC, successive approximation architecture ADC, that runs without a clock. Normally, when you have a SAR, you run a clock that's 12 or 16 times as fast as your sample rate, and voila, out pops your 12 or whatever number of bits you're looking for. In our case, there is no high-frequency clock. It's all self-timed, and out pops your 12-bit result. We also had a problem with delivering 0.25 volts with any efficiency, so we've come out with a line of IP for switch converters, buck converters, that will efficiently convert 2.5 volt I/O rails down to 0.25 volt, a 10x reduction, at very high efficiencies. We had to do that because people couldn't use our methods if they didn't have access to power. And finally, we've done a lot of work on SRAMs and UARTs. We have a UART that's actually self-timed. If you think about that for a minute, you'll say, wow, how does that work? Because UARTs are all about timing. One thing we can talk about over lunch. So, benefits of an always-on processor. Well, fast interrupt response. So I told you that we run 250 kilohertz at 0.25 volts, and I'm saying fast interrupt response time. But if you look at the Jackrabbit guys, they have a 15 to 25 microsecond penalty before they issue the first instruction, or the first clock of the 6th instruction interrupt entry service. I do it on the next clock. Yeah, the clocks are a little slow, but my latency is actually much less than theirs to get into the interrupts and do something in the interrupts. Also, you can, since you're always on, you can occasionally reach over and sample how your MPPT point is set on the harvester and see if you want to tweak it. We can do that as frequently as we want because we're not waking up and we're not paying a penalty for doing that. Now, we still use duty cycling for radios and things like that that have very high energy loads. But for everything else, we do the always-on paradigm. You can vary your performance. One of the things you can do with dial logic is you can turn up the voltage slowly or fast, and we'll just track along. We'll just start running faster and faster and faster as you do that. So what we do in software is we look at the remaining margin we have at the end of our workload. So we do the workload, and we look and see how long it is till we do the workload again. And if that is losing ground, that means we probably need to speed things up a little, so we jack the voltage up a little. If we're starting to gain on that margin and get more margin, we can take that opportunity to reduce power, lower the voltage a little bit. So this second-order control loop we actually run in software for tuning our voltage scale operation. And finally, since we are self-timed, there's this pay-as-you-go kind of energy. If we have a high-frequency oscillator, maybe it's a crystal, maybe it's just an RC oscillator, in the system, everybody turns that off when they go to sleep. We do that too. But on the other hand, we don't even turn it on in normal operation. We wake up, we measure the temperature, pressure, and humidity in a cornfield. We don't turn on the high-frequency clock to do that. We just run off of the processor clock. So you don't have to pay those penalties for being awake that you would have to pay with the Jackrabbits. Finally, for chip architecture, we're going to go through this really quickly. This is an SoC. It runs at 0.25 dial logic 90 LP, and it has a Cortex-M3 processor. You'll recognize these blocks if you're familiar with M3s. Now, the nice folks at ARM did a really good job in building an asynchronous interface between H-clock things and SWD clock things for the debugger, so we took advantage of that. We kept the DAP SWD clock logic in what I call high voltage, which is 1.2 volts. I know that's not very high voltage, but for us it is. And so we can hook up any debugger that we care to the SWD pins and just run. We've done Kyle, we've done OpenOCD. They all are happy running against a processor that has no clock tree. We also built our GPIO block at 0.25 volts, or in the dial domain. The reason we did that is we wanted to be able to run bit-bangy kinds of things at whatever the current processor speed is. So if I run this voltage up to 1.2 volts and I'm running 90 megahertz or 100 megahertz, I want to be able to bit-bang at that rate, at least to show off the fact that I can do that. So we built the GPIO in there. And then the other problem that we have to deal with is SRAM. We used conventional clocked SRAMs from TSMC. Nothing funny about them. They're a little bit higher energy than they need to be, but for the test chip, they were fine. What we do is we provide the clock they require from our asynchronous acknowledges. And so we essentially run those memories at whatever speed we're running the processor. So at 0.25, we're very occasionally kicking a memory off. We also do demand usage for them, so if we don't have a need to do a load or a restore to a bank in a given cycle, we don't even give it a clock. So finally, we have to go off and talk to some high voltage world things. We talk into various things in the high voltage world, and when we do, we go over an asynchronous bus and talk to a clock domain. The orangey stuff is all clocked conventional RTL, pos-edge clock kind of designs. We have a little bit on this chip. So we too built a chip, we too built a board to put it on, and this is what ours looks like. It has a test chip on it. The test chip is the 90 nanometer implementation, and it has some regulators on it. These regulators provide 3.3 volts for interfacing to the USB world. They have 2.5 volts for our I/O ring. They have the high voltage rail, 1.2 volts digital. And they have a dial domain voltage, which I show here as 0.25, but the little pot that's up in the top there lets me adjust that between 0.25 volts and 1.3 volts. And you'll see in the video that that's basically what we're doing. We're slewing that voltage on there. So we also have an FTDI module here. This is our interface to OpenOCD. This is where we get 5 volts, and we have some UART and front panel kind of things going through here. But we also have a standard CoreSite, 10-pin CoreSite connector. So I hooked up a U-Link adapter here, and I brought up Kyle, downloaded programs over and over and over, no problems with it. So this runs like any other Cortex M3 you've ever worked with. It just happens to run with no clock tree. Measured results. So I'm going to go through these again quickly as well. This is in TSMC 90 LP, and we are operating down to 5 microwatts on the processor. Our optimizations, we've done a lot of work since we taped out this chip, and we know that we could redo this chip with about a 30% reduction in power if we did it again, and our 55 nanometer chip is going to enjoy those optimizations. We work with standard Eclipse, Kyle, and Linux debug and development environments. We've shown that many times. We have an example where we hook up a solar cell, a PV cell, straight to the dial rail. So we're getting our 0.25 voltage, if you will, from a solar cell. No buck, no harvester, just the solar cell. Loaded with our chip, it runs about 0.45 volts. I think open circuit, it runs about 1.1. So we put enough load on it that it's running 0.45 volts. Well, we're happy to run at 0.45 volts. And so we can run the solar cell demo. I'll be happy to show it to you over lunch or on the side here. I'll show you running that on a solar cell. Our Gen 1 is basically the 90 LP chip that we put out with the old style of optimization. And so it starts at 5 microwatts, and at 200 microwatts, we're running about a megahertz or so. We run all the way up to 100 megahertz, and I have to tell you, at 100 megahertz, we are burning as much power as anybody else does at 100 megahertz once we're running. The other thing that people worry about with these sub-threshold or near-threshold products is sometimes they have a tendency to run away in temperature extremes. And so we did a lot of, during characterization, we did a lot of work looking at what happens to our circuits under extremes of temperature and voltage as well. And so what we found is there's very little variability in the operation of our parts over temperature. Interestingly enough, they tend to run a little faster when you warm them up. And so you can put your thumb on one and see the frequency counter climb just a little bit if it's sub-threshold. The other thing that happens to us, since we're completely dynamically voltage scaled, we pretty much don't care how bad the power supply may be. You can put a 100 millivolt sine wave on top of 500 millivolts DC supply, and we're going in and out of threshold all the time. We just keep running. Finally, a reference design. I'm going to skip over this one in aid of time. You can look at this eye chart, but this basically says that for 25 hertz fusion rates, we have more than enough power to do that real time over at 0.25 volts. Finally, we built another little test board with this. This one, as you see on the right, has a PV cell that's extremely small, and there's a quarter to kind of size everything. But that PV cell will run this chip and its cast of characters, the voltage regulators and such, that we bring along with it as a solar-operated device, no batteries involved. So I have a little video demonstration for you, and I would like for Lance to start up the video, and then while it's running, we'll take some questions.
Lance?
There he goes.
Okay, great.
So what you're going to see here is that we're showing there's an onboard frequency counter for this chip, and you're seeing the voltmeter on the side, so we've already moved up to about a half a volt. We're running about 9 megahertz here. I think we'll actually spin this all the way up. It won't take very long. So we're now running 30 megahertz at 0.8. Just climbing right on up. 1 volt, we're hitting about 60 megahertz.
So as this is running in the background, maybe we can have some questions over there on the left.
David Lau, Imagination Technologies.
Ah, okay.
How do you do manufacturing tests for self-timed circuits then?
Oh, dang, I forgot to tell you that. On the flow chart that I showed for our methodology, we actually have ATPG running on these asynchronous circuits. We have a scan clock. It looks for all the world like any other ATPG that you've done. We use Cadence ATPG tools to do it. Some of the patents that we filed are how we make that work. They're not quite through the issue office yet, so I can't talk too much about it, but I'd be happy to tell you some generalities on it. The generalities are that during the time that we're running ATPG, we actually treat this as a clock circuit. The clock trees on this are a little funny because, normally when you have a clock tree, you have a big driver fanning out to a whole bunch of loads. Our clock trees are exactly the opposite. They're a big act tree fanning out from a whole bunch of drivers back into a single point. So they're kind of the inverted thing, which means there's a lot of parallelism out here at very low power. So our clock tree, that we have one, to the extent that we have one, is inverted. But we can take advantage of that to do scan chain.
Okay, next.
Nathan Brookwood from Insight 64. If you're running in a direct energy harvesting mode, what happens to a product that's using voltaic cell and you have an eclipse or something else that would wipe out the solar source?
I think that's the timeliest question that I've ever received. So here's the thing. We've built an agricultural example, what I call the steel flower. You have this steel rod, you stick it in the ground, and on top is this PV cell and some electronics. And we measure the things you see on the evening news, except for wind speed. We measure temperature, pressure, humidity, all of those kind of things. And we do that once an hour, which means over 24 hours, there's a substantial number of those hours that are dark, much like a solar eclipse. But what we've done is we've put some fairly large supercaps on the board. We charge those up good and heavy during the daytime, and then we operate off of those. So that gives you an idea of how little power we use. We live through the night with that. During the daytime, we fire up the radio when we got good solar power, minus an eclipse, and go after it that way.
Okay, so one last short question.
Thank you.
Bruce Kailani from NVIDIA. So previous subthreshold chips have often used other methods like synchronous clocking techniques with robust delay variation tolerance schemes, such as non-overlapping two-phase or something.
Right.
I'm curious, like the traditional problem with completion detection logic is the switch capacitance overhead of basically assuming you're doing dual rail or something like that. Have you guys quantified the overhead of doing that compared to those more traditional approaches, and why did you end up with that design decision?
By overhead, are you referring to a clock performance overhead or an energy overhead?
Energy overhead.
Yeah, okay, so the energy overhead is actually really small because of the voltages that we're operating at, and we have not been able to measure anything significant from that in our simulations.
I guess I meant at ISO voltage compared to a more traditional.
Oh, well, I don't have a more traditional to compare to, so I don't really have a good A/B way to do that. I think you got me. I don't have an answer.
Okay, let's thank the speaker for a great presentation. Thank you, Dave.
Thank you.
Thank you.